Section 9.3 deals with relative rates of growth. Okay. So, we have talked about, the other day we talked about a reminder from pre-calc on how to find horizontal asymptotes, right? They were limits as x goes to infinity or negative infinity. And if the higher power was on top, then what would the limit go to? Higher on top, think about what's happening. Yeah, the one on top is getting huge. That means the top is growing faster than the bottom. It's going to go to infinity. If the higher power was on the bottom, that one goes to 0. It's like 1 over a million. It's really, really tiny, very close to 0. And if we have the same highest power on top and bottom, then it's the ratio of the coefficient is our limit, right? Well, we're going to use these same ideas to help us determine whether one function grows faster than another function. Basically what we were doing, what we were figuring out. And we end up with using this piece of information, these two pieces of information. There it is. There's my bracket. All right. So if I'm comparing f of x to g of x, and I want to know which function grows faster, and we're only interested when x is really huge, okay? We want to figure out which one's growing faster. Well, we talked about horizontal asymptotes. We took the limit as x goes to infinity of f of x over g of x. When do we get an answer of infinity? When f of x is growing faster. So if you do the limit as x approaches infinity of a function over another, and you get infinity, then the top one is growing faster than the bottom one. If we do that same limit as x goes to infinity, and the answer comes out to be 0, then which one's growing faster? The bottom. Easy enough. So if our limit comes out to be infinity, top is growing faster. And if our limit comes out to be 0, then the bottom is growing faster. Okay? And then, if we do our limit as x approaches infinity of f of x over g of x, and we get some value that is not equal to 0, that's like when we had x to the 5th over 3x to the 5th, then that is the case when they are growing at the same rate. So if it equals a number other than 0, then they are growing at the same rate. And that's all there is to it. So the only challenging part is getting through the limit. And now we have L'Hopital to help us with that if we have an indeterminate form. So let's look at our first example. Get that to move. There it is. And I have it written as a limit, but really what I'm asking is which function grows faster. Ln of x or e to the x? That's the question that's being asked. Okay? So we set up our limit as x goes to infinity of ln of x over e to the x. But if we know what our graph looks like, we have an idea already, don't we? Natural log of x is here, e to the x is here. Which one is getting higher faster? E to the x. And it will continue, but now we can prove this using calculus. So when we do this limit, what's the first thing we do? Yes. Very nice. Check to see if it's indeterminate, to see if we can use L'Hopital. The natural log of infinity gives us infinity. E to the infinity gives us infinity. Check. We can use L'Hopital. And so we reevaluate our limit as x approaches infinity of what over what? 1 over x over e to the x. And a little bit of a rewrite makes it easier to see what's happening here. We have the limit as x approaches infinity of 1 over x e to the x. Isn't that the same thing? All right, and when we let x get huge, what does this approach? Huge on the bottom. It's like 1 over a million, so that's going to approach 0. Okay, and if our limit comes out to be 0, then which one's growing faster? The bottom is growing faster. And remember to go back to the original ratio. So e to the x grows faster than natural log of x. Good. Okay, nothing too tricky. All right, let's look at another example. X to the fifth versus natural log of x. Again, I'm asking which function grows faster. And which do you think? I think x to the fifth, so our limit should come out to equal what this time? It should come out to be infinity. So let's go ahead and do it. When I plug in, I get infinity over infinity. L'Hopital can be used. So now I have the limit as x approaches infinity of what? 5x to the fourth over 1 over x. And with a rewrite, limit as x approaches infinity of 5x to the fifth, which approaches what? Infinity. As we expected, x to the fifth grows faster than natural log of x. Okay. This one, what would you expect? Do you need me to go back, Lauren? Was I too fast? Yes, absolutely. All right, let's go on to the next one. On this one, what would you expect our limit to come out to be? 0. You expect 3 to the x to grow faster than log base 3 of x, as do I. I'd like you to try it at your desk, please. Okay. And before we get any further, the reason I put this one on, thank you, is, do we remember these derivatives? 1 over that, and you're good. So the derivative of log base 3 of x is 1 over x times the natural log of 3. And the derivative of 3 to the x? That's it. Natural log of 3 times 3 to the x. And it always helps me to think of e to the x. E to the x, it comes out to be the derivative of e to the x, right? So it would be natural log of e times e to the x. That helps me remember. Just does. All right, so try this one at your desk, please. Okay, so here is my solution. I plug in my infinity, and I've got infinity over infinity, which is indeterminate. I take the derivative of the top over the derivative of the bottom with a small rewrite. We end up with 1 over x, natural log of 3 squared times 3 to the x, which all of our powers of x are in the bottom. So once again, we have 1 over infinity, which is 1 over a gigantic number, which approaches 0, meaning that the bottom function grows faster, so 3 to the x grows faster than log base 3 of x. Yes? All right. Okay. So let's just talk about this one. 3x to the fifth over 5x to the fifth. Which one is growing faster?
They're growing the same speed.
Okay. Let me get my question in. Faster. All right, well, using our little rules that we've been using and the ideas of horizontal asymptotes, we end up with that limit equaling what? 3/5. And when we get a value other than 0, it says that they're growing at the same rate, right? Does that make sense? Five x to the fifth, 3x to the fifth, which one should be growing faster? Yes. So, if we are only thinking about lower values of x, then 5x to the fifth is growing faster. But as we start dealing with gigantic numbers, when we get out to 650 million for our x, are we going to see that difference between a coefficient of 3 and a coefficient of 5? No. So when the values are super large, this ratio of 3 to 5 becomes negligible. So we are only interested when the values are huge. So it does make sense if we only consider gigantic values that we could say these are growing at the same rate.
Doesn't the difference become bigger?
But what you are multiplying by is not a big number. It's not a big difference between the two, right? It's only the difference of 5 to 3.
When compared to like however many billion.
When compared to however many billion, exactly. That 3 times something versus 5 times something, the difference between those two values is not going to be noticeable when we get that big. So I will say these are growing at the same rate when x is huge. And I'm going to put quotes around my same rate. Because it never will be exactly the same, but it will be unnoticeable, the difference between the two. Okay? In your book there is a bit of a proof. So if you're interested, you can go and look at that. But just having this idea in your head as to why we could say that they're growing at the same rate when those values are so big should be enough. All right, finally, the last one I want to do is sometimes it's cumbersome to compare one function to another function using L'Hopital because the derivatives get ugly, and if you have to do it again, the derivatives get even uglier. So one thing we can do is use what's called the transitivity of growing rates. So it's basically going back to the transitive property, which the transitive property says if A equals B and B equals C, then A equals C. All right. So when we want to do this for comparing growth rates, if f of x is growing at the same rate as h of x, and g of x is growing at the same rate as h of x, then f of x is growing at the same rate as g of x. Okay, so if we can compare to a function, to a third function, and apply this transitive property, it may make our job a little bit easier. So, my f of x is given here, my g of x is here, and I'm picking an h of x that's kind of a nice little easy function. Okay? All right, so if I can show that the limit as x approaches infinity of f of x over h of x, if I can do this limit and show that these two are growing at the same rate, and then I look at the limit as x approaches infinity of g of x compared to h of x, and I show those two are growing at the same rate, then wouldn't that imply that f of x is growing at the same rate as g of x? Okay, there's that transitive property. So after we find these two, we could theoretically explain it, but we will also show it algebraically by doing the limit as x approaches infinity of f of x over g of x would be the same as the limit as x approaches infinity of f of x over g of x, f of x over h of x, times what would I have to multiply that by to get my f of x over g of x? H of x over g of x. So what we'll do is we'll take the limit of f over h times the limit of h over g. Well, to get the limit of h over g, what do I do with this one? Just take the reciprocal. All right, so let's go ahead and do this. We are taking the limit as x goes to infinity of the square root of x squared plus 5 over x. All right, so we can apply L'Hopital, but we can apply our horizontal asymptote rules here. What's the actual power on the top? But it's x squared to the 1/2, so that is x to the first over x to the first. So what is the limit? It is 1. All right, and then when we do g of x over h of x, we'll have 2 root x minus 1 squared over x. So let's do the same little analysis. When I square the top, I'm going to get a 4x to what power?
First.
To the first. So I have 4x to the first over x to the first. That limit is 4. All right, and then finally, so right now, I have said that f and h grow at the same rate, and g and h grow at the same rate. So theoretically, I could say f and g grow at the same rate. But if we want to do it analytically and show the algebra, we would take the limit as x goes to infinity of, what did we get from f over h? 1 times 1/4. And it's not the limit anymore because we've already done the limit. The limit of f over h was 1 times the limit of h over g is 1/4. We get 1/4. So what does that mean? F and g grow at the same rate. All right. So your homework, as I already had you write down, was section 9.3, 1 through 15 odd. And that is a change from the assignment sheet. So it's a change from the website. All right, that is it for tonight.